Hello, my name is Matthew Newland, and this is our coding section for our adiabatic flame temperature. And before we begin, I made a document that has a list of all of our given values and our equations that we're planning to use for this particular coding, our adiabatic flame temperature. One thing I want to point out that I didn't really touch on in my previous video was our integrated heat capacity equation, or at least all of it, because what we did in our previous video are we found our hyperbolic integrals originally from this original heat capacity video or heat capacity equation, but we did not find the rest of it. And this whole equation is what we need, or is what our actual integrated hyperbolic or our actual integrated heat capacity. And just going down the list of our natural gas inputs, just as a reminder, we have our methane of 95%, our ethane of 4%, and our propane of 1%. And for our air, we have an excess air of 20%, and we also have our ratio of oxygen to nitrogen. And down here, we just have our methane reaction, because we're just going to use this as a reminder for our reaction. So from here, we can then split our screen, then go to our coding, our code laboratory. And one thing we want to point out originally, is that we have all of our systems and all of our tools. We have our chemistry tools. We have our NumPy for any numericals. We need to computate. We have SciPy optimized, and we're going to use a root function to find our adiabatic flame temperature. And we obviously have our tools. And another thing I want to point out before we start is that in previous videos, we only had one set of information that we would be drawing from, and usually that would be water. However, for this particular coding, we have multiple. We have methane, ethane, we have propane, our oxygen, nitrogen, carbon dioxide, and water. And all of this is expressed in an array, and we need to be aware of that when we're going forward. So a lot of our things are going to be expressed and commutated in arrays. So to start off, we're going to start off with writing out our integrated heat capacity function. So we'll define a function here and call it integrated heat capacity. And our function our variable we're gonna call it is our temperature. However, a lot of these functions in this particular video are gonna be quite simple because we're only gonna have a return function. And the thing we need to do here is then type out this entire equation here. So we'll do that as such. So it's going to be our A parameter times our T, our temperature, plus our B parameter, and then that's going to be multiplied by our C parameter divided by our NumPy function of a hyperbolic tangent, and then it's going to be our C parameter again divided by our temperature, and that's the first part. And then we'll have our D parameter multiplied by our E parameter multiplied by our NumPy function of tangent of the hyperbolic function again. So then it's going to be our E parameter multiplied all together. And you might be thinking, well, we don't have any values to these particular components in here. Our A, B, C, D, and E don't have any values. However, since we loaded our tools already, we all we need to do is call or use our chemistry properties to then call our to give them actual values. So what we're trying to find is our parameters, and there is a list of parameters that go from our heat capacity of an ideal gas, and it lists it from A to whatever function. I'm not quite sure how far it goes, but we're just going to use A through E. So it's going to be our our heat capacity of an ideal gas. So it's going to be capital P or capital C, lowercase p, and then of an ideal gas, and that is going to be our values. And so we're going to copy and paste that and then just put it with the rest of our function here. And that should be it. And then we're going to have this whole function divided by 1,000. So I'm going to explain why we need this divided by 1,000 in just a minute after we write out our enthalpy function. So we're going to find our enthalpy function as such, with T being our call function, and then we're going to have our heat of or enthalpy of formation, or heat of formation. It's going to be as such. It's going to be capital H, or heat or enthalpy of formation of an ideal gas, plus our integrated. Just going to put that back just a minute, and then it's going to be our integrated function, or integrated heat capacity function, as such, minus our initial value. So we're just going to put an initial value of 298 Kelvin, because this is an integration. So we need to have a lower parameter and a higher parameter. And whatever this higher T is going to be our higher parameter. And now back to this function. Why do we have it being divided by 1,000? Well, one thing you notice is that we have our heat of formation here, and this is actually in kmol. And similar ways of how it relates to kilograms to grams is that kmol is actually 1,000 moles instead of just 1 mole. So we need to include this while we're so we need to divide this whole thing by 1,000 to put it in the correct units. So these are our two functions that we're going to use for our to find our adiabatic temperature. So that looks good. So the next thing we want to do is then start defining our inputs and our outputs, and finding the mole relationship between those two. So what we want to do is have our moles of fuel, which is going to be our methane, ethane, and propane. So we're going to make a numpy array as such, and our first value is going to be our methane, and then our ethane, and then it's going to be our propane. Excuse me, choked up on my words. And this is going to be our percentages of moles. So it's going to be our methane is going to be 95%, and then our ethane is going to be 0.04% or 4%. Sorry, lost in the decimals, and then it's just going to be 1%. And this is our percentages of moles, our percentages of our methane, ethane, propane. So that is our function there, and then we're going to make a function, another function, that's going to be our fuel of, I should have went back up, our fuel of our CH. And what this particular function is going to do, its purpose is going to serve the number of moles of, or at least atoms that are represented in both methane, ethane, and propane. So what we want to do is we're going to create a multi-layered array here. So we're going to start with our methane. So it's going to be one carbon to 4 hydrogen. Ooh, didn't want to close that off just yet. And then it's going to be 2 carbons to 6 hydrogens. And then it's going to be 3 carbons to 8 hydrogens. And this should, did I miss him? No, I didn't. That's good. Sorry, I was blocking it there. And this will represent the amount of atoms, or that's going to be in our methane, ethane, and propane. And then, since we want our percentages to also represent what's going in, we're gonna do something a little weird here. We're gonna have our number of moles of carbon and our moles of hydrogen equal to a array multiplication of fuel, our percentage of fuel, or fuel percentages, multiplied by our array for fuel of CH and carbon and hydrogen. This will then give us two values, or give us values we want to then, we can then use to find our carbon dioxide, our water, and the rest of our inputs and outputs for our chemical equation. And the last thing we need to put in is excess air. So we're going to write that as such. So it's going to be 0.2. Because we have 20%, which this excess air just means there's 120% air coming in, because we want to represent how much extra air is getting pumped in, because we are assuming that we're having more air pumped in than necessary. So this is going to be our excess air, and then we can start defining what the rest of our moles are for each of our products and reactants. So we'll just start with carbon dioxide because it's an easy one. So our moles of carbon dioxide is going to be equal to the moles of our carbon. It's because carbon is the only atom in here that that's being represented. It's going to be our carbon dioxide is going to be equal to our number of moles of carbon, because for whatever number of moles of carbon we are putting in is going to be the same of what we're putting out. And there is no ratio between our moles of carbon dioxide and carbon and just regular carbon, because there's only one molecule in our right side of the equation that has carbon, so we can just immediately rule that off. Our next thing we want to do is then have our moles of water, which is going to be equal to our moles of hydrogen divided by 2, because there's 2 hydrogen being involved. And then we can use this to find our moles of oxygen, which is going to be equal to our moles of water, like that, divided by 2, plus our moles of CO2. And this whole function, and this whole left side, is going to be multiplied by our excess, which is going to be 1 plus our excess air. And then our moles of nitrogen will then be represented through the ratio between oxygen and nitrogen, which is going to be 79/21, multiplied by our moles of O2. And this is what we want for our mole representations of each of our substances. Just going to look back through it real quick just to make sure everything looks all right. All right, looks good. And now here comes the tricky part, because we need to set up a dot product. And a dot product is the product between two vectors. And we need to set this up in a very particular way. So we need to do our number of things going in is then going to be equal to a numpy concatenate. And a concatenate, what that's going to do is that it's going to combine the functions we put in our numpy arrays that we're going to put into this particular function. So what the two things we want to combine is our moles of fuel are that array, and then we're going to make an array inside of this. Oh, I almost messed this up. I need that there. And then we need another numpy array as such. And the two things we want represented now, since we have what's going in our left side of the equation, we have our fuel, which is being represented here. And then now we want our oxygen, our number of moles of oxygen, and our number of moles of nitrogen. And then what we need now is 2 zeros. Because the last two things that are being represented here is our CO2 and our H2, and our carbon dioxide and our water, and we want zeros for those. It's not liking something, sorry. Syntax error. Oh, I see what I did. Forgot a comma. So we'll just call that function again and see what, and just get rid of this one. So, and then we have our number of moles going out, which is going to be just another numpy array, and that's going to be equal to 3 zeros at the start. And then what we want now is we want our number of moles of oxygen multiplied by our excess air, because we need our excess air being represented in our right side of the equation. And then we need our number of moles of nitrogen, and then we need our number of moles of carbon dioxide, our number of moles of water. Sorry, almost messed that up. There we go. Okay, so this should, yeah, that all should be good. So these zeros will come into play when we're using our dot function. And the last thing we want to do before we call our root solver, the last thing we want to do is then define a function that will be used to represent our temperature as a vector. So what we want to do is then define a function, and we're just going to call it our equation. And we need a vector that goes into our root solver. So we're going to call this a vector, this thing we're going to draw from here. And then we're going to set our temperature value equal to this vector, and we need our first value that this vector is going to use. And then we want to return the function, and this is where our dot product is going to come in. Ooh, almost messed that up. We need an array. We need to return an array because that's what our root solver is going to take. So we need to set this as an array as well. So it's going to be our numpy dot product. And unlike other normal functions we have, it's going to do the product for us. So we just need to set two arrays in here. So what we need now is we need our enthalpy function. So it's going to be our h of t, and then next thing we need is our int function, our thing going in, or no, excuse me, our moles going out. Then, because we need this to also to represent our, in terms of our integration. So we have our first dot product, and then we have our second dot product, which is going to be dot, and then that's going to be our our enthalpy function again. But we're going to use the same value we have here, 298 Kelvin, because it's going to be our initial, where everything's starting before the reaction even takes place. This is our initial temperature, and then it's going to be n going in. Oh, actually, let's mess that up. Okay, so just one last check before I get myself confused. Looks like all the formatting's right. I'm just gonna get rid of that because simplicity. Okay, that looks good, and then we're gonna use our root solver. So we're gonna set our function to root, and then put in our function from here, and then we need an initial guess, and it really doesn't matter what this initial guess is. So we'll just expect this to be around 2000. Ooh, I messed something up here. What did I mess up? I think I forgot to define something, so hold on, let me look. Forgot to find something here. Oh, actually, before we go back, I need to call this again. I know that's not right, but we need this last part to get an actual value out of it instead of just a series of values. What did I mess up? Access error. So something is not being represented. Oh, I see what I did. I messed this up again. Okay, yeah, I forgot to put a return on our second function for our enthalpy. So that's why it's not working. And this is what we get. This is our adiabatic flame temperature from our code, using all of our chemistry tools and our props for methane, ethane, oxygen, nitrogen, propane, and everything else you see here. Using those values and then using our dot products and using the number of moles we found our adiabatic mole temperature, or adiabatic flame temperature, excuse me.